So, today we will start the topic of demodulation of FM signals. So, there are four methods which we will discuss for the demodulation of FM signal. First is frequency discrimination method or FM to AM conversion method. Second is zero crossing detector method. Third is PLL method, which you have also studied in your B lab. And the last one is phase discrimination or phase discrimination method. So, what is the main idea of demodulation, right? You have embedded, this is your message at the transmitter. What you did, you took your message signal and you took your carrier signal, and the modulator first converted it to a FM modulated signal or PM modulated signal. We take a particular case of FM, and all the things which we have done for FM can also be done for the PM with slight modification. So, at the transmitter, what you did, you have just generated a FM signal, and at the receiver we again try to get this message signal back, because all the message signal is residing here, right. You vary some of the property of your carrier signal, and for the case of FM we change the frequency deviation. Frequency deviation is directly proportional to your MT. So, here we use a demodulator which will provide you, which will extract the message signal from your FM signal. So, let us discuss the frequency discrimination method in detail. Frequency discrimination method or FM to AM conversion method. Since we know that in FM signal the information resides in the instantaneous frequency of your FM signal. An instantaneous frequency of your FM signal follows this equation, that FIT is equal to FC plus KFMT. So, we need a frequency selective network such that if you feed your FM signal to it, the output must be proportional to your frequency deviation or instantaneous frequency, because instantaneous frequency is nothing but some constant. So, you can always remove this constant. So, the output is either proportional to your frequency deviation or instantaneous frequency will provide you your message signal back, right, which in turn will give you output as proportional to your message signal. So, it will work as a demodulator. Why we are calling a frequency selective network? Because its output depends on the frequency. So, this transfer function of FSM will also depend or will also be a function of its frequency of your input signal. So, this is possible, such type of requirement can be met, or this is possible if the transfer function of this frequency selective network satisfies this property, that magnitude of the transfer function of HF should have this form AF plus B, where A and B are constant, and this must be true for the entire band, entire FM band, right. So, our aim is to find out the frequency selective networks who who possesses the transfer function with this property, that magnitude of the transfer function is AF plus B. Why if you have such a transfer function will give you signal which is proportional to MT, let us see it. So, if this is your FM signal, right, the equation, this is your FM waveform with instantaneous frequency as this. So, if this our LTI system, this is LTI system, we know the output will be magnitude of the FM signal multiplied with the magnitude of the response of this LTI system. So, this is AC, right. The output is, let me write it in the output if of this LTI system, if you remember from your if you take the only, we are interested only in the magnitude of the output. So, the magnitude will be this, right. We are interested in the magnitude of the output of this LTI system, which will satisfy this property. So, magnitude is only AC. So, the output of this system will be AC into mod of HF, and mod of HF we have said that will satisfy this property. So, we put our AC AF plus B, AC into AF plus B here, and we know that instantaneous frequency F satisfy this property. So, we put F from here. So, it will have AC AFC plus AKF MT plus B. So, it can be also written as AC AFC plus AC into B plus AC AKF into MT. This is a DC term because it is not a function of time, and if you pass this signal through a DC blocker, we will have only this term will be discarded and the output will be AC AKF into MT, which is directly proportional to MT. So, we are successfully able to demodulate this XFM, frequency modulated signal. So, first we require a frequency selective network with transfer function as AF plus B, magnitude of transfer function as AF plus B, then we pass it through a, we take its magnitude or envelope, and then we pass it through a DC blocker. So, we will be able to extract the message signal. So, so we are summarizing it here that this type of system are also known as frequency discriminator. Rather, if we define a precise, if I give you a precise definition of a frequency discriminator, any frequency selective network which possesses such characteristic, or the output of a device possesses such characteristic, will be termed as a frequency discriminator. And here you see that it is directly proportional to the frequency deviation, because if this is instantaneous frequency, it is directly proportional to the, this is frequency deviation, right. So, it will be directly proportional to the if slope is A, this is A times the delta F, or A times F's IT minus F's. So, this is the definition of frequency discriminator, and it is not a perfect frequency differentiator, but we can call it a frequency differentiator. Okay. So, because if you plot the output and this characteristics, it is a little different from this one, but still we can call it a frequency discriminator. Now, the question is how to devise such circuit which gives you a transfer function or frequency selective network of type this, right. Because any frequency selective network which possesses such a characteristic, such a transfer function, would be able to demodulate your frequency modulated waveform. So, there are various possible circuit with such characteristics. This is for characteristics, and the simplest one is the one with transfer function as HF is equal to J2 pi f. And if you remember, this is nothing but an ideal differentiator. So, an ideal differentiator can be used in order to demodulate our FM signal. So, let us see how can we use that. So, this is your FM waveform, we pass it through a differentiator, and if you pass it through a differentiator, what it does, if you just differentiate this, you will get this signal, right. So, if you observe these two equations, here the message resides in frequency change, right, in frequency deviation. And here if you see, the message now also resides in the amplitude of your output. I mean at the output of your differentiator, now message also reside in the amplitude. So, what we do, we next extract the envelope of this. So, we pass it through envelope detector, and this is the magnitude, right, or this is the amplitude or the envelope. So, the output of your ED would be this, and if we block the DC component, the output will be this. So, we started with a theoretical or a conceptual system, that we want such a system that whose transfer function possesses such a quality, or AF whose magnitude of transfer function is AF plus B, would be able to give you empty. So, this is all conceptual, but now we have seen that a differentiator, an ideal differentiator, can serve the purpose, right. So, now let us I mean here we have assumed that our amplitude, when we received your FM waveform, the AC, the magnitude, there was no distortion in the amplitude of the FM signal, but due to noise and channel there might be some distortion, and if AC were a function of time, then the output, as you see, the output is AC 2 pi k of mt. So, if our AC were function of time, you will not have an output which is directly proportional to mt, it will have some distortion. So, we should make sure that when we receive our FM signal, there are no time variation, or there is no amplitude distortion. So, if you remember, we have discussed that amplitude distortion can be taken care by a band pass limiter, right. So, we put a band pass limiter before the differentiator. So, complete block diagram of FM demodulator using FM conversion is as follows. We receive a frequency modulated signal, we pass it through a band pass limiter, then we differentiate it, and we take its magnet, its envelope, and then we pass it through a DC blocker, and we get a demodulated output that is directly proportional to mt, or precisely if you can write, you can write AC 2 pi k of mt, AC 2 pi k of mt. So, this is the complete block diagram of your FM demodulator using frequency differentiator, discriminator, sorry, or the FM to AM conversion. But there is one important point which you must remember, that in order to perfectly find the magnitude or the envelope, in order to extract the envelope, we must satisfy this condition that the envelope must be always positive. I hope you remember this from your previous discussions, that AC 2 pi f C, it should not be T, I think, right? Yeah. There is some mistake, so just correct it. C 2 pi f C plus 2 pi k f mt plus 2 pi k of mt must be greater than equal to 0, or 2 pi f c, it must be f c. So, just 2 pi f c plus 2 pi k of mt must be greater than equal to 0, correct? Or this is possible, this is true when your mod of k of mt is always less than equal to fc. This is very easy to verify this, and in detail we have discussed in the class, so I am skipping that details. So, you can see that this is true when mod of k of mt is quite less than fc, or max of KFMT is less than or equal to FC, and this is nothing but max frequency deviation. So, if your max frequency deviation is quite less than the carrier frequency of the FM signal, then you can use the envelope detector for the demodulation of the FM signal. So, this point you have to notice. This is generally true. If you see that frequency deviation is generally quite less the carrier frequency. So, next we discuss the other method. So,